All right, so we're going to continue our conversation on finding volumes by introducing one more technique for finding volumes. So let's take a look. So let's say we have a function that behaves this way. And we have, say, an A and a B. And this is the region that we're interested in revolving around an axis. Now, if we were to choose to revolve this around the x-axis, well, no problem. It's very easy to see that we would integrate this guy with respect to x, integrating from a to b, and revolving those rectangles around the x-axis would produce a disk. And we could then use the disk method to find the volume. However, what if we were actually interested in the solid that emerges by rotating this region about the y-axis? Now, looking at this region, I hope that you can see that integrating this region with respect to x is eminently superior to integrating it with respect to y. Right? There's a consistent upper function, a consistent lower function, and there's a left x value and a right x value. However, if we insist on integrating this with respect to x, and we should, think about what shape would emerge if we rotate this rectangle around the y-axis. It's not going to be a disk or a washer. It's going to be what's called a shell, a cylindrical shell. So no problem. I mean, this isn't a problem, right? Because all we have to do is just come up with the formula for the volume of that shell, and then using an integral, we just add up this sequence of concentric shells that constitute the actual solid. So how would we do this? Well, what we want is the volume of one shell. So we'll call it dV, right? Tiny amount of volume. Well, how would you find the volume of that shell? Well, it would be essentially the surface area of the shell multiplied by the thickness of the shell. Right? That should give us the volume of that shell. Okay, the thickness is very easy. If you look at our graph, you can see the thickness of that shell is just going to be dx, right? It's the thickness of that rectangle, and in fact, that's infinitely thin, which would really make an infinitely thin shell. So the thickness of the shell itself is dx. But what is the surface area of that shell? Well, the surface area of the shell is the circumference of the shell times the height of the shell. That would give us the surface area of the shell. So what's the circumference? Well, for that we need a notion of radius. So the circumference would be 2 pi times the radius. And what's the height of the shell? Let's just call it h. And here's the height of the shell on the shell. There's our h. So, okay, very good. How does that relate to the actual function here? Well, our radius is this dimension here. It's the radius of the revolution, right? This rectangle moves around the axis of rotation, which is the y-axis in this drawing, with the radius r. And the height is that measure right there, which in this case would just be the height of the function. So putting all these ingredients together, we can see that the tiny amount of volume, dV, would be the surface area of the shell, which is the circumference of the shell, 2 pi r, times the height of the shell. So all of that is the surface area of the shell. now multiplied by the thickness of the shell, which is dx. And therefore, the volume of the solid is simply the sum of all the dv's, or the integral, which would be the integral from a to b of 2 pi rh dx. Now, I just want to point out that this doesn't supplant the washer or disk method that we know and love. This is just another method which frequently is a much better decision to use, but very often the disk and washer is a much better decision. So one of the things that we're going to see throughout the next few examples is how to make the right decision about whether you should use washers or disks, which is one method, or shells, which is the other main method. Okay, so let's summarize the shells method for finding volumes. Okay, so we're going to see two formulas, one for dx, one for dy, which are virtually the same. In the dx case here, r and h must be in terms of x. So the radius and the height are in terms of x, of course. And the alternative here is integrating with respect to y. Okay, big surprise, our first example is finding a volume. So let's see what we're working with here. This is going to be the graph of a parabola. And if you recall, we can find the vertex of a parabola by calculating this particular formula. You can also just take the derivative and see where its critical point is. So the vertex of this parabola has an x-coordinate of 2, and if we plug the 2 into this, we can see that we get a y value of 4. So vertex of 2, 4, and it's an upside-down parabola because the coefficient of x squared is negative. All right, we can also locate the x-intercepts of this parabola pretty easily by factoring the x. So we get 4 minus x. We can see there's an x-intercept of 0 and an x-intercept of 4. So there's our parabola, and the line y equals x is just a diagonal like that, which means that the region we're dealing with is that region there. All right. We are also told that we're rotating around the y-axis. It is true that we are in the section on volumes by cylindrical shells, which means that we're obviously going to be working out this example using cylindrical shells. However, let's practice right now the skill of determining what the best technique is to use. So the first, and in fact truly the only decision that you make when approaching these problems, is looking at the region and deciding whether or not you want to integrate with respect to x or with respect to y. And this particular region, it's very clear that integrating with respect to x is the best option. Integrating with respect to x means that is the shape of our rectangles, with the narrow dimension being dx. So if we rotate this around the y-axis, we will get the shape of a cylindrical shell. So we're going to use the shells method. There's a little mnemonic that a former calculus student brought to my attention a couple years ago, which is once you draw your sample rectangle, if it's parallel to the axis of rotation, then use the shells method. So think of it as para-shell. if it's perpendicular to the axis of rotation, which would be the case if we were going around the x-axis in this case, then you use the disk or washer method, and the mnemonic being perpendicular. So here, our sample rectangle is para-shell with the axis of rotation, so we're using Shell's method. So our volume is going to be the integral of something dx, because that's the only decision we've made, is choosing the dx. But because we're choosing to integrate with respect to x, it means that the bounds of our integral are going to be x values. And the integrand is going to be 2 pi times r and h. So we also need an r and an h. So let's start by finding the bounds. We're just going to set the curves equal to each other and solve. Okay, this is a quadratic equation, so we'll just move everything to one side. And we can see that our bounds are going to be x equals 0 and x equals 3. So looking at our graph, there's our 3, and of course there's the 0 where they intersect. Okay, so therefore our volume is 0 to 3, 2 pi RH dx. So we just need our r and our h. Well, let's look closely at this picture. The axis of rotation is the y-axis. So capital R is the distance from the axis of rotation to the sample rectangle. And in this case, that distance we're just going to call x, because it's just a horizontal distance to the point we're interested in. The height, h, is just the upper function here minus the lower function. Well, the upper function was that parabola, and the lower function was the line y equals x. So our h is in fact 3x minus x squared, which means that our volume integral is 0 to 3, 2 pi, r, which is x, h, the height, 3x minus x squared. And there's our setup. So again, if this were a setup only problem, that would be the best place to stop. But let's finish this integral. We can distribute, so we get 6 pi x squared minus 2 pi x cubed. And integrating will give us 2 pi x cubed minus pi over 2 x to the fourth from 0 to 3. So plugging 3 into this guy, 3 cubed is 27, 2 of those is 54, minus 3 to the 4 is 81, so we get 81 pi over 2. And then plugging 0 in, just will be 0 minus 0, which is very convenient. And 54 doubled is 108, so that's 27 away from 81. So this is 27 pi over 2. Okay, so let's find the volume of this solid that emerges by rotating this region about the x-axis. So our first decision is whether to integrate with respect to x or with respect to y. And again, I hope this is very clear that this region ought to be integrated with respect to y. But just for a moment, let's pretend like we insisted on integrating with respect to x. I mean, it would be unfair to acknowledge that we don't all secretly want to integrate with respect to x. That's the variable we're used to for this kind of thing. But if we insisted on integrating with respect to x, then a sample rectangle would look like this. And while rotating that around would of course create a washer shape, Okay. It's perpendicular to the axis of rotation. There's no clear upper and lower function here. In fact, we'd probably have to just split this into two parts. And once it's split into two parts, then we have a nice upper and lower function here, and we have another upper and lower function here, and you can add those together and you're off and running. But this is definitely not the efficient way to handle it. And I'm a fan of efficiency. So let's go with integrating with respect to y. We have a very clear, consistent rightmost function and leftmost, and a nice beginning 0 and a nice ending at root pi. Our sample rectangle is para-shell to the axis of rotation, so we will be using the shells method. So our volume will be the integral from something to something, but let's go over here and put dy in. That is the one and only decision that we made, and everything else is automatically induced from that. So that means that the bounds of our integral must be y values. Well, we can see it starts at 0 and ends at radical pi. And the formula here is 2 pi rh. So we just need r and h. Okay, well, our r is the radius of the rotation. It always reads outward from the axis of rotation toward the rectangle. So there's our r. And we can see here that r is equal to y. Well, what is our h? That's the height of the shell, which in this case would be the height of this, or the width, if you wish, of this rectangle. Okay, remember, this is forming a shell. So there's our h dimension, and the radius is just the radius of the shell. So our height is going to be the rightmost function, which is sine of y squared, minus the leftmost function, which is 0. Okay, so our volume is the integral from 0 to rad pi of 2 pi times y times sine of y squared dy. So that's our setup, but of course this problem asked us to find the volume, so let's go all the way down to get an answer. And this one's going to require u substitution. So here we'll let u equal y squared. So du is 2y dy. Then our integral becomes the integral of, we'll update the bounds in a moment. We have a 2 pi times y dy, which is du over 2, times sine of u. Oh, that's very nice. These 2's cancel. Let's also update our bounds. So when y is equal to 0, u is equal to 0. And when y is equal to rad pi, u is equal to pi. All right. Before I go on, you may be wondering, that's a little odd. Why didn't he put the du on the far right of the integrand? Usually du is kind of on the right of our integrals. It's sort of like the punctuation. Well, I did that on purpose, just to bring up this bit of conversation, actually. It's very important that we acknowledge that du is a factor of an integral, okay? It needs to be handled when you're doing substitution. That transition from dx to du, or in this case dy to du, needs to be handled. It's not important that it's always on the right of the integral. It's convention that we do that, but it can be right in the middle or even the first term of the integral. It just needs to be there. I'll admit that it looks a little nicer when it's on the right, so there we are. And we know our substitution was successful, so let's actually carry out the integration. Antiderivative of pi sine of u is negative pi cosine of u. We'll plug pi in there. and 0. Cosine of pi is -1. Cosine of 0 is 1. So we get 2 pi. Final answer.
Excellent.
All right, here we are with another volume problem. And this one should be familiar to you because we worked it out as one of our examples in the last lecture. But back then we only knew the disks and washers method, so we were forced to integrate this one with respect to y in order to create a washer shape, which involved converting this function into a function x of y. And the integral itself was non-trivial when we worked it out, but we eventually got an answer of 225 pi over 2. What we're going to do here is solve the same problem, but now we know about cylindrical shells, and we're going to work it out that way, and we're going to see not only will it be simpler than it was before, but of course we're going to get the right answer. So let's see. First of all, as always, our first decision is to integrate with respect to x or with respect to y. And in this region, it doesn't really matter. We, of course, integrated it with respect to y last time. So this time, let's integrate with respect to x. And also, the function here is given y in terms of x. So that'll minimize the amount of algebra we need to do as well. Okay, so our sample rectangle is para-shell with our axis of rotation. So we're using the shells method here. And we've settled on integrating with respect to x, which means we need x value bounds. Those are clearly 0 to 3. And our integrand will be 2 pi rh dx. So we just need r and h, of course. Well, what is r? R is this length right there. So how do we articulate that length? Well, it consists of a fixed component here of 2 units and a variable component here, which we're going to just call x. It's a horizontal distance, so that would be x, which means our r will be 2 plus x. All right, and now what about our height, h? Well, that's just the height of this rectangle. And we can see that's upper function minus lower function. Lower function is 0, so it's really just the upper function here. H will be 9 minus x squared. So our volume will be the integral from 0 to 3 of 2 pi times r, which is 2 plus x, times h, which is 9 minus x squared, dx. So let's work out this integral and hope that we get 225 pi over 2. I think this is going to call for some foliage. Okay, let's integrate this friendly thing. So 18 integrates to 18x minus 2/3 x cubed plus 9/2 x squared minus 1/4 x to the 4. And our bounds are 0 to 3. Okay, let's plug 3 in here. So we have 2 pi times 18 times 3 is 54 minus 2 times 9, which is 18, plus 9 times 9, 81 over 2, minus 81 over 4. And if we plug 0 in, we just get 0. So that's great. Okay, so what are we working with here? 54 minus 18, that's 36. Plus 81/2 minus 81/4, that would just be 81/4. So if we distribute for a moment, we'll get 72 pi plus 81 pi over 2. So 72 doubles to 144. 144 plus 81 is 225 pi over 2. So math is awesome.